Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss the properties of moist air. As you know, the air which surrounds us is not a dry air. It is a moist air, and moist air consists of dry air and water vapor in the form of vapor. Now, air is also a mixture of different gases, and major components of air are nitrogen and oxygen. I will not like to go into the details because this you must have done several times, volume to volume ratio and weight to weight ratio. Air has traces of carbon dioxide, argon and many other gases, but they are in the form of traces only. The major components of air are nitrogen and oxygen. Air which surrounds us also contains water vapor. Now, water is the partial pressure of the water. I will give you some idea. Partial pressure of water is of the order of, let us say, 3 kilopascal. So, out of 100 kilopascal, 3 kilopascal is the partial pressure of water, and as per the Dalton's law, the total pressure in a given volume is the algebraic sum of the pressure exerted by the individual constituent. So, air is considered as a pure substance. So, pressure of air and pressure of water, partial pressure of water will give us the total pressure of air. Now, we will go by the definition of psychrometry. Psychrometry is the study of atmospheric air and its associated water vapor. So, thermodynamic study on this, the mixture of pure air and the water vapor is known as psychrometry, and psychrometry is very helpful in air conditioning processes, because in air conditioning normally we maintain the temperature and relative humidity. Relative humidity is denoted by phi also, it is denoted by RH also. So, we deal with the temperature and relative humidity. When we talk about the humidity, the presence of water immediately comes into the picture. So, psychrometry is the study of atmospheric air and its associated water vapor. It is a science which deals with the properties of air water vapor mixture, and that is called psychrometry. In the air mixture, I have already explained this. The third point, they behave as per the Dalton's law, and the total pressure in the mixture is the partial pressure of air and partial pressure of water. In engineering practice, there are some mixtures where one of the constituent is vapor. Since the vapor in these mixtures is very low partial pressure, it is in the superheated state. In some of the mixtures, in not all the mixtures, in some of the mixtures, when it is there in very small amount, it has very low partial pressure. When the partial pressure of vapor, I have told you earlier also, that the pressure is less than 10 kilopascal, the vapor can be considered as a gas. That is why in psychrometric analysis, the water vapor is considered as a gas. So, we often use PV is equal to RT relation for water vapor. But the same relation we do not use in the case of steam turbines, analysis of steam turbines, because there the pressure is high and temperature is not that high that the vapor can be considered as a gas. When the temperature of any vapor is greater than 2 times the critical temperature, in that case it is also considered as a gas. There are two conditions for considering vapor as a gas: either pressure is less than 10 kilopascal or temperature is 2 times the critical temperature. This temperature is in Kelvin, not in degree centigrade. So, in steam turbines, this requirement is not fulfilled, this requirement is also not fulfilled. That is why in gas turbines steam turbines, not gas turbines, in steam turbines we use steam tables. We do not use, for steam turbines we do not use this relation. However, in the case of air conditioning, because the pressure is less than, in most of the cases I will give you some numerical values also, is less than 10 kilopascal, PV is equal to RT relation is used. Now, the third thing, the very remarkable thing is here is in gas vapor mixture, the composition may change. I mean, if I have, let us say, 970 grams of air, dry air, and 30 grams of water in this dry air, right, at particular temperature, T degree centigrade, T1 degree centigrade. Now, if I change the temperature to T2 degree centigrade, now let us, it is on higher side actually, this is 985 and 15. So, 15 grams of water in 985 grams of air, that is 1 kg of air and at a particular temperature, this is the composition. If we change the temperature, this composition may change. 985 may remain same, this may reduce to 10 grams. So, 10 grams is associated with the 985 grams or it may increase to 20 grams. So, 20 grams is associated with the 985 grams. Now, these values I have taken from RefProf 7, this is NIST based software, where the temperature, I have taken temperature, saturation temperature starting from 2 degree centigrade to 52 degree centigrade. This pressure, saturation pressure of steam or water vapor is given on the right side. At, let us say, at 4 degree centigrade, saturation pressure is only 0.814 and this room is suppose 26 degree centigrade. At 26 degree centigrade, the saturation pressure is 3.364 kilopascal. Now, this is the saturation pressure at 26 degree centigrade, right. So, you can imagine the order of pressure. So, the room pressure is again 101, so let us say 100 kilopascal. So, major chunk of pressure comes from the air pressure and vapor contribution is only 3.364 kilopascal, and here definitely the vapor can be considered as a gas. So, I have taken priorly I have taken properties starting from temperature 2 to 50 degrees centigrade, because we will be needing these values frequently in subsequent lectures. Now, enthalpy of liquid at these temperature is also taken. Enthalpy is in kilojoules per kg, and enthalpy of the gas and latent heat, all these 4 values have been noted earlier, and frequently we will be referring these values while exercising on psychometry. Now, there is a terminology in psychometry like dry bulb temperature, DBT. Now, dry bulb temperature is normal temperature used with a thermometer, measured by using thermometer. So, normal thermometer, that is liquid in glass thermometer, you must have seen liquid in glass thermometer, or which is used for the medical purpose also. It has a bulb and bulb is dry. There is no coating on the bulb, there is no fluid on the bulb, and the temperature indicated by this liquid in glass thermometer is known as DBT. So, normally when we say the temperature of this room is 20 degrees centigrade or 25 degrees centigrade, it is nothing but DBT of the room. So, DBT, whenever we say the temperature of room is 25 degrees centigrade, it is DBT of the room is 25 degrees centigrade. So, normal liquid in glass thermometer measures the dry bulb temperature. Another temperature is wet bulb temperature. Wet bulb temperature. Now, if I put a wick in this bulb, if I put a wick or some wet cloth over the surface and blow air, normally in order to find wet bulb temperature, the velocity of air has to be between 5 to 10 meters per second. Then what is going to happen? The moment the air is blown over the wet cloth, the evaporation of water from the surface will take place, and for the purpose of evaporation of water from the surface, the heat will be taken from the bulb and the temperature of bulb will go down. So, normally the wet bulb temperature is less than DBT, and this is known as wet bulb depression. The difference, suppose the dry bulb temperature is 25 degree, DBT is 25 degree centigrade, wet bulb temperature is let us say 18 degree centigrade. So, wet bulb depression is 25 minus 18, 7 degree centigrade. Now, this wet bulb temperature of 7 degree centigrade, if it is more, then what does it indicate? If it is less, then what does it indicate? And if there is no change, I mean both are equal, then what does it indicate? When dry bulb temperature is equal to wet bulb temperature, it means even when the wick is or the wet cloth is placed on the bulb, air is blown, there is no evaporation from the surface. No evaporation of the surface means the air surrounding this bulb is already saturated with water. If the air is already saturated with water or 100% saturation is there will not be any evaporation from the surface of the bulb. It means the humidity is 100%, and which is known as relative humidity. This I will explain in subsequently. So, humidity, the air is humid. If this temperature difference is too large, suppose this is 8, so depression will be 17 degree. It means there is a lot of evaporation from the surface by the movement of this air, and therefore, the air surrounding this bulb is dry, it is not wet. It is dry, it is not wet. So, this gives us the status of the air, right. There is a machine which is known as hygrometer. Now, hygrometer, there are two types of hygrometer, one is sling type of hygrometer. In sling type of hygrometer, we just rotate the hygrometer, this the thermometer covered with the wet cloth is rotated very fast, and when it is rotated for certain time period, there is a dip in temperature. When the temperature is stabilized, then we measure the wet bulb temperature. That is one kind of hygrometer. Another hygrometer is aspirating hydrometer, where this bulb is placed in a wet medium and air is blown over it, maybe through a fan or through some other arrangement. In that case, also we get wet bulb temperature. So, these two temperatures are very important for us. These two temperatures are very important for us because immediately they gives us idea about the state of the air in the environment. Now, the third is dew point temperature. Now, if I keep on reducing the temperature of this room, right, after certain temperature, the water vapor in this room will start precipitating. This precipitation will start, and that temperature, that particular temperature is known as dew point temperature, and difference between dry bulb temperature and dew point temperature is dew point depression. So, if the humidity in this room is high, the dew point temperature will be higher. If the humidity in this room, humidity means the water content, if the humidity in this room is low, the dew point temperature will also be lower. If you look at here, now in this table, suppose I have saturated vapor, I will give you an example. If I have saturated vapor at 24 degree centigrade, at 24 degree centigrade, if I have a saturated vapor, the saturation pressure is 2.986. If I reduce this temperature, if I reduce from 24 to 20, then partial pressure of the vapor will reduce to 2.339 kilopascal. Partial pressure is reducing. If this is saturated, this is also 100% saturated. Partial pressure is reducing, it means amount of air, amount of water in the air. This is amount of water vapor. So, water vapor is also getting condensed. I am repeating. Suppose I have air at 24 degrees centigrade. The partial pressure of the water vapor in the air is 2.986 kilopascal. I have noted from there. Now, the temperature of this air is reduced to 20 degrees centigrade. the partial pressure or saturation pressure of the water vapor will also reduce to 2.339 kilopascal. So, at this 24 degree centigrade, the air is a mixture of partial pressure of air plus partial pressure of water vapor. That is the total pressure, right. Now, partial pressure of the vapor is reducing when we are reducing the partial pressure of water vapor is reducing when we are reducing the temperature. It means some amount of vapor is getting condensed. So, some amount of vapor is condensed, that is why the partial pressure of the water vapor is reducing, and we can say that this is the dew point, because this is 100% saturated. So, this is a dew point of air which is already saturated. So, now specific humidity of the air is denoted by omega or W. It is mass of the vapor, ratio of mass of the vapor and mass of the dry air in a given volume or per unit volume or a given volume of air, mass of the water vapor and mass of air. Now, here we can always use ideal gas equation. So, P V volume is equal to R V and T, temperature is same in both the cases. So, W is equal to MRT is equal to MV, R, V and T. So, MV we can always take as PV, partial pressure of the vapor, multiplied by volume divided by gas constant for vapor multiplied by temperature of vapor. Similarly, we can take these values for air, partial pressure of air, volume of air is same, gas constant for air and temperature of air. Now, these two will be cancelled out and we will be getting the expression as PV by RV divided by PA by RA. Now, gas constant is always universal gas constant by molecular mass. So, it is going to be equal to MV by MA multiplied by PV by PA. Now, molecular mass of water is 18. So, W is 18 by 29, approximately for air it is approximately 29, and universal gas constant is same for all the gases, and PV by PA. Now, this PV by PA, and we also know that the total pressure is equal to, this is total pressure is equal to PA plus PV. So, W is equal to 0.622 PV divided by total pressure minus PV. This is known as specific humidity of air. Humidity ratio is same. In some of the books, this is written as specific humidity, and some of the books it is indicated as humidity ratio, but that is this is a very important parameter in air conditioning. Later on you will come to know that this is a very important parameter in air conditioning. Now, absolute humidity and relative humidity ratios, specific humidity, humidity ratio, absolute humidity. Absolute humidity is the mass of water vapor associated per unit volume. So, it is on volumetric basis. Absolute humidity, nowadays it is not used as a parameter. Relative humidity is important. It is used everywhere. In fact, in order to express the state of moisture in the air, this term relative humidity is used. Now, relative humidity is denoted by RH or phi is equal to mass of the air, mass of the vapor in the air and mass of the vapor in the air when air is saturated. again we will be using the relation PV is equal to RT, right? Sorry, PV is equal to MRT. So, MV is equal to pressure is same, pressure is PV, V, R is same, T is same, and MS is equal to PS V over RT. So, at the same temperature, mass of the vapor present in a sample of a given volume and mass of the vapor in a given volume for the saturation at the same temperature. So, if I put these values here, then phi is equal to PVV by RT divided by PSV over RT, then these will be cancelled out and relative humidity is PV by PS. Now, if I go back to the previous slides, suppose here at 24 degrees centigrade, partial pressure of the vapor is 0.2986. So, partial pressure of the vapor is 0.2986 at 24 degrees centigrade and saturation pressure is also 2.986. So, air is 100% saturated. Now, if I ask you to find the partial pressure of the vapor when the relative humidity of the air is 50%. 50% at 24 degrees centigrade dBT. Now, in this case, what I am going to do, I will take relative humidity 50% as PV I do not know, PVS I can take from here 24 degrees centigrade, it is 2.986 and multiplication of 2.986 with 0.5 will give 1.493. This will give us the value of partial pressure in kilopascal. Now, if I want to find the mass of water vapor in the air, total pressure is 100 kilopascal, then W is 0.622. We will use the specific humidity expression for specific humidity we have driven earlier, PV divided by P minus PV or P total pressure minus PV. PV we have got from here. Now, we will be putting the value of PV here, total pressure is known to us. We can find the kilograms of air associated with the kilograms of per kg kilograms of dry air, because the unit is kg of water per kg of air, dry air. So, we will get how much water is associated with the per kg of dry air. Now, third one is saturation ratio. Nowadays, this is not used. It is again saturation ratio is the is equal to the specific humidity of the air when specific humidity when the air is saturated, right. So, if we take specific humidity of air 0.622 PV divided by P minus PV and specific humidity of the air when it is saturated, that PVS divided by P minus PVS, and then we are going to have PV by PVS, P minus PVS and P minus PV. We are going to get this expression for this saturation ratio, and this is nothing but relative humidity, and P is much larger than PVS. So, this expression is not 1 but very close to 1, it is very close to 1. But so, therefore, nowadays we only go for relative humidity in order to express the state of the air, or if you want to have some calculate some amount of water, then we go for specific humidity. Now, adiabatic saturation. Now, adiabatic saturation is one of the way. One way is I told you hygrometer can be used for finding out the the wet bulb temperature. Now, another another method of finding out the the humidity of the entering air is through adiabatic saturation process. In adiabatic saturation process, there is a passage of infinite length. There is a passage of infinite length, and vapor is entering from this side having T1, temperature T1, specific humidity W1 and enthalpy H1. So, any air which is entering from this side will have certain temperature, specific humidity and enthalpy. Now, this air will leave from this side. This is the temperature of water, and this is the specific humidity on this side, enthalpy on this side and temperature on this side. When this air is completely saturated, the T2 will be equal to TW. When T2 will be equal to TW, and we will say that air is, because during this course evaporation from here will take place and water will get mixed with the air till it is 100% saturated, right. If we do the energy balance, that is going to be equal to H1 is equal to H1 plus W2 minus W1 multiplied by HW is equal to H2. The enthalpy of air leaving this side is equal to the enthalpy of air entering from this side plus enthalpy added to air by virtue of evaporation of water from this water at the bottom of the passage. Now, H1 is, because it is a mixture of liquid and vapor, so it is going to be TdV tribal 1 plus W1 HS1. We are taking TdV1 because for enthalpy, because enthalpy is change in enthalpy. Change in enthalpy is Cp delta T. Now, Cp T2 minus T1. Here T1 we are assuming to be 0. So, this is temperature in degree centigrade. So, T1 is assumed to be 0. So, enthalpy at temperature 1 is assumed to be 0. So, it becomes Cp T2. Now, Cp for air again we are assuming 1, though it is 1.005. So, when we are Cp for air is assuming 1, the enthalpy at this temperature is going to be TdB1. This is specific humidity multiplied by the enthalpy of saturated vapor. Now, why we are taking enthalpy of saturated vapor? In this case, now here, it means if the temperature of incoming air is at 40 degree centigrade, enthalpy of saturated vapor is 2573.5, but in most of the cases the vapor is superheated. So, this energy of superheat is also neglected here in this expression. Similarly, W2 minus W1 enthalpy of the water which is added here is equal to again TB2 plus W2 HS2. Now, this is the expression. If we derive the final expression out of it for W1 is equal to W2 HS2 minus HW T2 minus T1, W2 HS2 minus HW T2 minus T1 divided by HS1 minus HW. Now, if there is 100% saturation, then we can definitely find the value of W2. These values are already available with us. We can find the specific humidity of incoming air. This is another method of finding out specific humidity of incoming air, and this method is known as adiabatic saturation method. Now, sensible heat of air. Now, sensible heat is the heat added and there is a change in temperature and there is no change in the phase. Both conditions should be fulfilled. So, sensible heat is equal to always Cp T2 minus T1. And total heat is equal to the sensible heat and latent heat of air. Suppose the room temperature is 27 degrees centigrade, and if I inject steam of 27 degrees centigrade, the room temperature will not change, but the total heat of the room will change because there is a latent heat addition in the room. So, I think that is all for today. Next time we will start with the psychometric chart. Thank you.